morning, chemists. Are you guys ready to learn more about these interesting allylic systems? So we were discussing our allylic carbocation, radical, and carbanion, and we said they have this interesting stability. We're first looking at the electrons, though. Where can we put them into what orbitals? And so we said we can put electrons into these bonding orbitals here, where we are lowering the energy overall. And then we do put electrons into non-bonding orbitals for the radical and for the carbanion, but we put nothing into our anti-bonding. And so we've lowered the energy overall of these electrons, and we have nothing in this anti-bonding, so we can form bonds and we can have these unpaired electrons. So as we look at this, in our non-bonding, we have a node. And so remember what a node is. It's an area where we would expect no electron density. So it's an area where there is zero probability of finding an electron. So in this non-bonding, we have an area right in the middle on that middle carbon where we would expect to find no electron density, which makes sense. When we have our, so let's first look at our carbanion. So we have here, one of our resonance forms has the negative charge on this carbon, and the other resonance form has the negative charge on this carbon. So for our two resonance forms, notice that there's no negative charge in the middle. There's no negative charge in the middle, so you can see here the red area is congregating really mostly on the two edges. It's mostly on carbons 1 and 3. And then the same thing for our carbocation. So for our carbocation, we have a positive charge on one carbon, a positive charge on the other carbon for the two resonance forms. And so you can see that blue area of low electron density, that is delocalized over carbons 1 and 3. And same thing for our radical, we are delocalizing that unpaired electron over those two carbons, carbon 1 and 3, and so we can see that electron density in this electrostatic potential map. And so here, again, we're looking at the node for the non-bonding electrons. The non-bonding electrons, remember what those are. For the radical, the non-bonding electron would be this unpaired electron. For the carbanion, the non-bonding would be these two electrons that are not involved in a bond. They are the lone pair. So our pi2 has that node, and then we have that excess or deficiency electron density. We don't see it on the middle carbon. Questions on that? All right, moving on to 14-2 now. Here's our first reaction. So we said we have this allylic system that's very reactive. What kind of reactions can we do? So here's our first one. If we have an allylic system, so here double bond with a methyl, if we have that in the presence of, so let's say Br2, but it has to be a low concentration of it, and then we would have just our regular solvent, carbon tetrachloride. If we have this allylic system, we can put a bromine here on this carbon, on the allylic carbon. So this is similar to another reaction. If we had this same exact alkene, but instead we have bromine, just a regular high concentration of it, instead of a low concentration, a high concentration of it, still with carbon tetrachloride, what reaction are we going to do? Well, we know we're going to do that anti-bromination, right? So we're going to add a bromine to both of those carbons. So this is a reaction we saw back in chapter 12. In chapter 12, we said we can do this bromination in the presence of bromine, or we can do a chlorination in the presence of chlorine with carbon tetrachloride. We're going to do the anti-addition of those two bromine atoms. But now I'm telling you, if we have a low concentration of the bromine, instead of adding it in that anti-addition to carbons 1 and 2, instead we add the bromine, just one of them, to carbon 3. Instead, we're adding one bromine to carbon 3. So the difference here is that we're talking about an ionic reaction. This is an ionic halogenation versus this being a radical halogenation. And so for our radical halogenation here, we are going to keep the concentration of the whatever the halogen is, we're going to keep that low because that's going to inhibit the ionic mechanism. So to inhibit the ionic mechanism, we use low concentrations of that halogen so that we can do a monohalogenation. Just add one halogen atom next to the double bond to the allylic carbon. So here we're not doing the same reaction as in chapter 12. We're doing a different reaction based on having low concentrations. But for this reaction to occur, we also are going to need here peroxide or light. So some kind of a peroxide, oxygen-oxygen bond, or light in order to initiate this reaction, because it's a radical reaction. So we need a radical initiator, which would be the peroxide. Or we need light, which we know is H nu. So what kind of reagent can we use for this? How do we get low concentrations of the halogen? Well, we get low concentrations of the halogen using NBS. So NBS, if I just write that over the arrow, that means N-bromo-6-cinnamide. Again, we still dissolve it in carbon tetrachloride. So one reaction, the one we were just talking about, we would use NBS with carbon tetrachloride, but that is a source of bromine. And that's going to allow us to put this bromine there on carbon 3. So what happens here is that we have our N-bromo-6-cinnamide, NBS, and that's going to be in the presence of trace amounts of the acid HBr. That's going to form bromine. And so this bromine here is going to be in a low concentration. Why is it in a low concentration? Because this has low solubility in carbon tetrachloride. Low solubility of NBS and carbon tetrachloride, that will keep the concentration of bromine low in solution. If we added in just straight bromine, then that would be a high concentration, but we keep the concentration low by using NBS dissolved in carbon tetrachloride. So only a little bit of that can turn into bromine at a time. So we keep our concentration very low of that bromine, which is what we need to do this radical reaction. So what's the mechanism for this? We said we have some HBr. So our oxygen gets protonated. We know our oxygens are basic, so they go for a proton. And so when that oxygen gets protonated, we have here a nitrogen that's bonded to bromine. Now that's a polarized bond based on electronegativities. So the electronegativity value for nitrogen is 3.0, and for bromine is 2.8. So it's slightly polar. Not really, but we have a difference in electronegativity enough that when we draw the other resonance form where we get a positive charge on the nitrogen rather than a positive charge on oxygen, that's enough for us to be pulling away electron density, making this into an electrophile. So our bromine now is an electrophile. So we have bromide. Where did we get the bromide? From where we our HBr in the beginning. So the bromide comes in, picks up that electrophile. Nitrogen gets to keep its electrons, and so nitrogen is happy. We get this neutral intermediate, where now we have our bromine Remember, this is going to be a low concentration of this bromine, but we know one of these can be partial positive, one of these can be partial negative. We can break that bond easily there. We can polarize that, pulling electron density. But here, we're not doing an ionic reaction. So here, we don't need this to be a polarized bond. We can polarize it, but we don't need it to be because we're going to use this in a radical reaction. So we have a low concentration of bromine used in a radical reaction, so we don't need to polarize that bond, that bromine-bromine bond. But let's look at what we have here. This is similar to an enol. Remember our enol that can tautomerize? So we have an enol where we can move around the electron. So from the middle of this bond to the proton, from the middle of this bond into that bond, we can tautomerize, giving us an amide. So here, when we see a carbonyl with a nitrogen, we've made an amide bond out of that product. So our intermediate will tautomerize to form the amide that is more stable. So it's similar to an enol, but this is called an immenol. So this is how we make our bromine from NBS. We have our NBS. It's dissolved in carbon tetrachloride. We lose that bromine from the NBS and bromo-6-cinnamide, and we make Br2. But that's just to make the bromine. We haven't done the reaction yet. So how can we do this radical reaction? Well, we have our NBS, we have our carbon tetrachloride. Our NBS will form this low concentration of bromine. And so then we use something to initiate the reaction. So we can use light, or we can use the peroxide. Either one is fine to initiate the reaction. So here we are initiating this with light, but either one would be fine. And we're doing our initiation like we learned before, back in chapter 3. Remember, nothing goes away. So now look, this is a radical reaction. We're not talking about ionic. We're not talking about forming positive charges, negative charges, partial positive, partial negative. Now we're breaking that bond where we end up with these two bromine atoms. Remember, Br2 is just bromine, the molecule. But we make these two atoms. Again, this is all review stuff. All right, so then we're talking about our propagation. Now this is what's new. So we said it's very easy to break that bond between the allylic carbon and the allylic hydrogen. That bond is easy to break. That's what we started off this chapter saying. It's easy for us to break that bond when it's an allylic CH bond. And so for that allylic CH bond, we need 3 arrows, one from the unpaired electron on the bromine into the middle, one from the middle of the carbon-hydrogen bond into the middle, and one from the middle of the carbon-hydrogen bond to that carbon. And so we end up with this allylic radical. And we know that the allylic radical can be stabilized by resonance. So by resonance, from that unpaired electron into the middle, from the middle of that carbon-carbon double bond into the middle, and from the middle of that bond onto that carbon. We can draw these resonance forms, the same resonance forms that we talked about before. So we can break this bond. It's easily broken. And as we break the bond, we are making an allylic radical that is stabilized by resonance. So then we have our two radicals. Either one of those can react with our bromine. What did we say for our radical reactions? We always wanted in our propagation steps to use something that had unpaired electrons, so something that's radical, with something that had no unpaired electrons, right? Something with unpaired electrons with something that has no unpaired electrons. Again, the same thing. We're not going to use the bromine atom. We're going to use the bromine molecule so that we can propagate this reaction. If we use the molecule, then we make more of those bromine atoms. And remember, that can go back to react again in propagation step 1. So here's our propagation step 1, propagation step 2. Remember that we always have to make something with an unpaired electron in order to continue with the reaction. If you don't make something with an unpaired electron, what is that? A termination step. So if you try to bring together a bromine atom with this allylic radical, you're going to be doing a termination step, and you remember what those termination steps are from 351. So both of them will react here. If these two are different, then we're going to get two different products. If these two are the same, then we're going to get one product. They've just shown you one product because based on this just being R, those two would be the same. So here's our general mechanism for reacting here. In alkene, so here we have cyclohexene, reacting it with NBS, and we get this bromine added in the allylic position. So if I call this 1, 2, 3, you can see there's only one kind of allylic position. It didn't matter if we put the bromine here on 3 or what I'll call 6. They're going to be the exact same product. Those two allylic radicals would be identical. So it doesn't matter there. We'd only get one single product there. But it's not always going to be true that we only get one single product. We have to actually look at the allylic radical. So you need to draw your intermediates in this reaction. So here we have 1-octene. So I'm going to draw this out, but I'm just doing the exact same thing that we see here at the top. And so with NBS, and look, we have our radical initiator, peroxide. So with that or light, either one would be fine. But in the presence of NBS, we make our bromine. And so we're going to be getting here this radical, where we've put an unpaired electron on this carbon that is the allylic carbon. We know that that can be stabilized by resonance, though. So from the unpaired electron into the middle of that bond, from the middle of the double bond into the middle of the bond beside it, and then from the middle of that bond to the carbon on the end. We end up with now a double bond here and an unpaired electron on the end. So if I number this 1, 2, 3, 4, those carbons can't move. All I'm doing is changing my double bond from being between 1 and 2 to being between 2 and 3. And so the unpaired electron also moves. It moves from being on carbon 3 to being on carbon 1. It can't move anywhere else. We can't do a double bond on 4, between 4, 5, 3, and 4, nothing like that. The only place we can do a reaction is here at this allylic hydrogen. So then we know that when we add in bromine, when we add in NBS, we're going to have some bromine there. And so these both can react with bromine in our second propagation step. And so we end up with bromine here, along with bromine here. Are these two different allylic radicals? Yes. Are these two different products? Yes. These allylic radicals are different from one another, and so we're going to get two products formed there. Now we have to think about stereochemistry. We know that here for this could be cis or trans, but we know trans is major, right? So we'll just draw it as trans because we know that's the most stable conformation for that double bond. But cis or trans would be possible there, but trans would be major. And there's no chiral carbon, so we've thought about both kinds of stereochemistry. But now looking at this other one, we have no cis-trans for this double bond, right? It's on the end, but we do have a chiral carbon. We know carbon 3 is chiral, and so we put an asterisk there, and we can put racemic underneath it. Why is it racemic? Well, remember that for our radical carbon, so carbon 3, is trigonal planar. And so if that's trigonal planar, our bromine can attack from the top or the bottom or front back, which means that we have both of those products, one where the bromine is on a wedge on carbon 3 and one where it is on a dash on carbon 3, meaning that it is a racemic product. So you can draw one with the, we'll just do the dash, that's easier, and then write racemic, or you can put that asterisk there and write racemic underneath it. So it turns out for this, our product, we get 28% yield of this racemic product. So 14% of both of those enantiomers. And then we get a 72% yield of this other product, mixture of cis and trans, but as we said, trans is going to be major. Why are we seeing this 72% yield here for this product? It's most likely due to the stability of the alkene product. The alkene, this internal alkene is more stable than this terminal alkene. And so based on that, it's most likely that the alkene that we get here, this intermediate, is going to be major based on the stability of the alkene of the intermediate. So that's going to lead to more of that product. Questions on this radical allylic halogenation? All right, then moving on, that's our radical reaction. So just radical reaction with NBS, peroxide, light. Then we have an SN1. So here we're talking about SN1. What do we know about SN1? Remember, it's stepwise reaction. SN2, that was our concerted reaction. So for this reaction, we have an allylic halide. So again, let me just draw what you see here. So we'll call this 1, 2, 3, 4. So in this reaction here, the first step always is our leaving group leaves, right? That's our first step for this SN1. And so here, if our leaving group leaves, we end up with this intermediate where we have a positive charge on carbon 1, and we have a double bond still between carbons 2 and 3. So as we do the reaction, we know we end up with this intermediate that could be stabilized by resonance. How is our arrow drawn? Well, now we're talking about ionic. We're not talking about radical. So from the middle of this bond into the middle of this bond, where now we end up with a positive charge here on carbon 3. So we have these two resonance forms. There are no more resonance forms that we can draw here, but we end up with these two resonance forms where then if the reaction happens at carbon 1, we're adding in water as our nucleophile. So if water attacks, so that oxygen lone pair attacking carbon 1 versus it attacking carbon 3, those are the two different products that we could get. So if it attacks carbon 1, you know that this would be 2 more steps here. 2 steps here. But if it attacks carbon 1, we end up with this OH on carbon 1. If it attacks carbon 3, then we end up with an OH on carbon 3. So those would be the 2 products that we could get there. But notice that there's something else here. So we start off with 1-chloro-2-butene, we end up with these 2 products. But what if we started off with 3-chloro-1-butene? What if we started off the exact same reaction, but a different starting material? So for this, I'm going to number this, not how it should be for the name. I'm going to number this in the same way as everything else that's on the slide, so that you can see that when we do this reaction and our leaving group leaves, we end up with this carbocation here. And so with that carbocation, we can go ahead and do the resonance forms, where again, we would end up with the same 2 final products. So it doesn't matter if we start off with 1-chloro-2-butene or 3-chloro-1-butene, we're going to end up with the same product mixture because we end up with the same carbocations. We go from 3-chloro-butene to one of these carbocations that can access the other one, or 1-chloro-2-butene that gets to one of these carbocations that can access the other one through resonance. So both of these resonance forms end up with 2 products here. What's the difference in our 2 products? Well, we know that we could have here for this, we could have cis or trans, but we know trans is major. So I've drawn a trans. And then what about for our other product? Well, our other product, carbon 3, that is a chirocarbon. And what are we looking at? A trigonal planar carbocation. That's why it's so important for you to know what the shape is. If this is trigonal planar at carbon 3, anytime you have a positive charge or a radical on a carbon, it's trigonal planar. So the water can attack from the top or the bottom or front back, which means that this is going to be a racemic mixture. So we get a racemic mixture of 3-butene-2-ol. But it doesn't matter what the starting material is, we end up with this mixture of 2 products. So for this, the major product is actually going to be this product, because we're going through a more stable carbocation. Because we went from a secondary carbocation instead of a primary. Questions on that? All right, so that's our SN1. We know it's stepwise. We know the mechanism of SN1 now, and we also remember that we could do like hydride shifts, but now we're not talking about hydride shifts. We're talking about resonance, which is different from hydride shifts. Resonance and hydride shifts, 2 different things. Hydride shifts, you're actually moving a hydrogen around. A resonance form, you're only moving around electrons. Only electrons are moving when you're doing resonance. So only double bonds, triple bonds, negative charge, positive charge, radical. Those are the only things that move around, electrons. But for a hydride shift or an alkyl shift, you know you're actually moving around a hydrogen or an alkyl group. Those are 2 different things. So we talked about SN1. Let's talk about SN2. We know SN2, not stepwise, but concerted. We know what the mechanism looks like for that. So for example, here from the lone pair to that carbon and breaking that bond, because we know that carbon has a partial positive because it's bonded to chlorine. We know that this is a good reaction, right? When we have a primary alkyl halide or haloalkane, when it's primary, we know that that's good. That's a good rate, very fast rate for the SN2. If we change that from being just a regular primary haloalkane to being now an allylic haloalkane, it's still primary. Look at how much faster the rate is. The exact same reaction, but now the rate is 73 times faster. 73 times faster. Why? Well, as I said, partial positive on the carbon, partial negative on the chlorine. We're pulling electron density toward the chlorine. But remember that this is an sp2 hybridized carbon. And what did we say about sp2 hybridized carbons? We said they are electron withdrawing. And so we're pulling electron density toward that carbon also. So there are two electron withdrawing groups, making this carbon now more electrophilic. It's more electrophilic because it has two electron withdrawing groups on it. So it's a much faster rate. So for our rate of SN2, we said, sorry, not primary. We said our tertiary is going to be the slowest rate. It really doesn't even happen. We can't do SN2 with tertiary. We can do it with secondary, and primary or methyl we said were the fastest. Well, now we know allylic is even better. Allylic has a faster rate than primary because for allylic, now we have these two electron withdrawing groups. Questions on the SN2? All right, 14-4. Now we're going to talk about how to make allylic organometallic reagents. Here we're going to make them from other organometallics. So we're going to make allylic organometallic reagents from other organometallic reagents. So here we have N-butyllithium. We know that that's a strong base. And we said that when we have a hydrogen bonded to an allylic carbon, that is acidic. So here, the blue hydrogens, they are acidic. So then the solvent here is called TMEDA. This is TMEDA. Tetramethyl ethylene diamine. So you can just write TMEDA, that suffices. But this is called a solvating agent. It's going to help everything to dissolve, and it's going to help when we have these ions. So what do? When we deprotonate, we're going to be taking away one of these hydrogens, and so we're going to end up with, here, I'll draw it here, a negative charge on one of these carbons because we deprotonated it. What has a positive charge? Remember our lithium? So our lithium will have a positive charge. We can draw a resonance form with this though. This is acidic because the product is stabilized by resonance. Allylic hydrogens are acidic because the conjugate base is stabilized by resonance. Remember we said if we can stabilize that conjugate base, That makes it easier for us to make it. We want to make a weak base. Something can be a strong acid because it has a weak base. So our base here is stabilized by resonance. What's our resonance form? Well, from the lone pair into the middle of the bond, right? We start where we have an excess of electron density. Where you have a negative charge, that's an excess of electron density. And then from the lone pair to this carbon on the end, we don't move around carbon. So 1, 2, 3. We don't change where any of the carbons are. The only thing we can change is where the electrons are. So now we have the electrons on carbon 1, and we have a double bond between carbons 2 and 3. Those are our two resonance forms. We know that here, if we have this negative, we have to have something with a positive. So we have lithium with a positive charge. So here we have made now an organometallic reagent. We made it from N-butyllithium. We use an organometallic reagent to make an allylic organometallic reagent. The other way to draw this, we know, would be here, where we are showing the bond, but we put in partial charges. Now, these two are equivalent. Remember how we talked about equivalent resonance forms? These two are equivalent resonance forms. So if this was our intermediate here, you know you would only make one product because these two resonance forms are equivalent. So equivalent resonance forms here. Let me go back. When we had these two resonance forms, these are non-equivalent. These two are not equivalent, so we ended up with two products. They're not equivalent, right? We said the secondary was our major intermediate, our major resonance form, which led to one of these products. But these two are not equivalent to one another, right? They are different resonance forms. So you have to pay attention to the resonance forms as you are drawing your product. All right, so that's how we can make allylic organometallic reagents from other organometallic reagents. So we add in N-butyllithium. Well, how do we make them from allylic halides? So here we have this 3-bromo-1-propene. How is this made? This can be made from this, right, where we just add in our NBS. That NBS reaction would make this allylic halide. So then with our allylic halide, we add in magnesium, metal, not the ion. And so then we can turn our allylic halide, so bromide, into the Grignard. So partial positive, partial negative, turns into partial negative, partial positive, and you know how to draw the resonance forms for this. We could have done the same reaction if we had added in lithium metal. So magnesium or lithium, but then that would give us our alkyl lithium reagent. So we know how to use these as nucleophiles now in all the reactions we already discussed. But you have to think about your resonance forms. So you might have resonance forms with your nucleophile, with the alkyl lithium, allylic lithium, or allylic Grignard reagent that you made. You might have resonance forms, and so you might have different nucleophiles. Different nucleophiles will lead to different products, but you know how to use those. Questions on that? All right, then we're moving on to 14-5. So that everything we just talked about was what if we have one double bond and it's an allylic system. Now we're talking about if we have two double bonds. If we have a diene, two double bonds. So with two double bonds, If they're separated by one single bond, we'd call it a conjugated diene. Conjugated dienes are very stable because they have greater resonance stabilization. So we're going to talk a lot about these conjugated dienes here. Then we have another situation where we have two double bonds that are separated by these saturated carbons. Remember, saturated carbons, the sp3 hybridized alkane carbons. We would call that non-conjugated. And then our third thing is an alene, where our double bonds share one carbon atom. So let me show you what each of those situations are. So we said we have conjugated diene. A conjugated diene would be this, where we have double, single, double. That repeating unit, double bond, single bond, double bond. That is called conjugation. That is stable. So here we have 1,3-butadiene is conjugated. It is a stable system because it is conjugated. It has this resonance stabilization, extended pi system. Then we have here 1,4-pentadiene. Double bond, double bond. Notice that there is a saturated carbon in between. So double, single, single, double. This is non-conjugated. That's not as stable. And then our last case is what's called an alene. So we have a double bond. We put a dot in the middle and then another double bond. This is saying that we have 3 carbons. So 1, 2, 3, where carbon 2 is in a double bond to carbons on both sides. So carbon 2 is sp hybridized, where we're using one of those p orbitals to get this overlap. And then we have a front and back overlap also for another p orbital for that carbon. Carbon 2 is sp hybridized instead of sp2. So for these different systems, we can see that this extended pi system allows for this delocalized electron density, right? We can see all that red area, we've delocalized our electron density, versus for 1,4-pentadiene, we have our electron density only on one side and only on the other. We don't delocalize that electron density. We know that delocalizing makes something more stable. So we're going to talk a lot about conjugated and non-conjugated double bonds. You don't really see the alene very often, but it's also non-conjugated. All right, how do we name our dienes? Well, our dienes are named basically the same way we would name our alkenes. We look for the longest carbon chain. If your longest carbon chain contains both of the alkenes, you name it as a diene. Look for your longest carbon chain. If it doesn't include both carbons, all 4 carbons of these alkenes, then it's named a different way, and we'll talk about that in a minute. But if your longest chain contains both of the double bonds, you number it from the end. That gets you to a double bond as quickly as possible. We can add in our cis trans, we can add in our EZ for our alkenes. So remember all that, that didn't go away. But we need to give a number for where each of the alkenes are. So here we would drop the Ne. So we have pentane, pentane. We can drop the Ne and put diene on the end. So it's pentadiene. Pentadiene. And then we need a number. So carbon 1 and carbon 3 have our alkenes. And then we know trans, what does that apply to? It only applies to this double bond between 3 and 4. There's no cis trans for the double bond between 1 and 2. You already know that. Here for this second one, we have a 7-carbon chain. So we number getting it to the alkene as quickly as possible. So it's a 2,4-heptadiene. So they wrote cis2 trans 4. way to write this would be 2Z 4E, close parentheses, 2,4 heptadiene. Right? 2Z 4E. This is a Z alkene. This is an E alkene. 2,4 heptadiene. Now, the same as what we did before applies, so you could do 2Z 4E dash hepta dash 2,4 dash diene. Either one is fine. All right, let's look at our next one. We have other things that could be added in also. So here we see that this is a Z alkene. What is the Z alkene? Well, it's this alkene here. But 4-bromo 1,3 pentadiene or 4-bromo penta 1,3 diene. 4-bromo penta, no dash, 1,3 diene. So bromo penta, that's all together, and then 1,3 diene. All right, so for all of these are all conjugated dienes up here. Now let's look here. Here we have a non-conjugated diene because we have carbon 3 in between our dienes. So here, cis 1,4 heptadiene, or you could add in EZ there. So Z would be fine there, or you could put 4Z for that name. We can also have them in a ring. So here, this would be cyclohexadiene. So 1,3 cyclohexadiene. Or here we have 1,4 cycloheptadiene. This is non-conjugated. So this would be conjugated because of this portion of it, double, single, double. It doesn't matter that we have these other carbons on the other side. This would still be a conjugated diene. And then the other one would be non-conjugated. Because our shortest distance here between the two, we don't have the double, single, double repeating. All right, let's do another example here. So is this conjugated? Yes. It's a conjugated diene. Now we need to number it. So we number it getting to a diene as quickly as possible. An alkene as quickly as possible. So we have a 7-carbon chain. Do we have EZ? We have EZ for both of them. So for this double bond, hopefully you can see at this point, I don't need to go through that. This is E, and this one is Z. So for the full name here, it would be 2E, 4Z, 1, 3, 4, 5, tetrachloro. And then we can do 2,4 heptadiene, or we can do hepta 2,4 diene. Questions on any of these?
So if there were 2 carbons in between the 2 double bonds, then it wouldn't be called a diene anymore?
No, it's still called a diene. It's not a conjugated diene.
Okay,
It's
so
a
it's like at least
non-conjugated.
1 carbon in between?
So the only way, so here we have this long carbon chain. This is a conjugated diene.
Mm-hmm.
This is still a diene, but it's a non-conjugated diene.
Okay. Thank you.
Other questions? All right. Then as we continue this, we need to look at here what happens if our longest carbon chain is not part of those two carbons, right? Those two alkenes, I should say. So here our longest carbon chain is 6 carbons. One of the alkenes isn't included, right? Here's carbon 1, 2 of the substituent. So our longest carbon chain would be called a hex 1ene. And then we have an ethylidene as a substituent. But for that ethylidene coming off of carbon 3, we know that that is an E alkene. And so this whole name would be E3-ethylidene, hex 1ene, or 3-ethylidene 1-hexene. Your longest carbon chain is your longest carbon chain. If it includes the diene, great. If it doesn't, so here we have an 11 carbon chain, doesn't include the diene at all. The diene is a substituent. So we have our undecane. And so for our undecane here, we have this on carbon 6. We can put the trans here, or we can put this into the parentheses because there's no there's no discrepancy there. We know where the trans is. The only trans double bond is in that 1,3-butadiene null. YL on the end because it is a substituent. Then we have here, again, this trans could be inside of the parentheses. So there's no number needed because there's only one substituent and it has to be on carbon 1 of this cyclohexane. But we need a number for where the alkenes are in this butadiene. And so it's a buta 1,3-dienyl, or what you saw over here, 1,3-butadienyl. Either way is fine. Those two are interchangeable. All right, now for our last example here, we have an alcohol, and we know the alcohol is the highest priority. And so if the alcohol is highest priority, then this becomes a substituent on the alcohol chain. So we have an ethanol, a 2-carbon alcohol chain, where on carbon 1, we have the alcohol, and on carbon 2, we have this cyclohexadiene. It's a substituent, and the double bond is between, if we call this 1, 2, 3, 4, then the double bond is between carbons 1 and 2 and 3 and 4. Questions on any of these? All right. So then let's talk about stability. So remember, we've talked about now 2 times before heats of hydrogenation. Now this is our 3rd time seeing it. And so we said if we hydrogenate an alkene, so here's our hydrogenation, we're going to release some heat. We're going to release about 30 kilocalories per mole of heat. If we have a non-conjugated diene, so here non-conjugated for both, we have each diene giving us about 30.3 kilocalories per mole of energy as we hydrogenate. So it's roughly double what we would see for one alkene. So any additional alkenes, then we're going to see that they're going to release about 30 kilocalories per mole of energy. But if we go from a non-conjugated diene to a conjugated diene, a conjugated diene doesn't release 60. It releases a little bit less than 60 kilocalories per mole of energy. If we had non-conjugated diene, then it would kind of be like 2 isolated double bonds, where we would release about 60 kilocalories per mole of energy. But we release less energy because it's a little bit more stable. We would say it's resonance stabilization. A conjugated diene is a little bit more stable, about 3.5 kilocalories per mole of energy more stable than a non-conjugated diene. Why is this true? Why do we see this resonance stabilization? Well, it's because we get this overlap of these pi bonds. So here we're talking about this 1,3-butadiene. So we know that each of these carbons has a p orbital on it, and with that p orbital, we get this overlap above and below that allows for us to make this double bond. And then again over here, overlap above and below that allows us to make this double bond. So if I call this 1, 2, 3, 4, this would be my carbon 1, 2, 3, and 4. So we see those pi bonds that we're forming. But with that, when it is conjugated, we can get this weak pi overlap between carbons 2 and 3. Carbons 2 and 3, yeah, that's a sigma bond, but we get this weak pi interaction because technically we still have these two p orbitals that can overlap above and below, but it's a weak pi overlap. It's not the same as making a pi bond. It's not the same as making a pi bond, but this is what stabilizes the system. If we had a non-conjugated diene, we'd have a p orbital here, a p orbital here, a p orbital here, p orbital here. We wouldn't be able to see that weak pi overlap in the middle, right? There's no weak pi overlap in the middle. But because we have a conjugated diene, we see a weak pi overlap between carbons 2 and 3. So with this diene, because we have this weak pi overlap, we can raise the barrier to rotation. So the barrier to rotation, how much energy do we have to put in to rotate around that double bond? That is increased because of this weak pi overlap. So we usually can rotate easily around single bonds, right? We can easily rotate around any single bond. But now it's a little more difficult for us to rotate around a single bond when it is a diene, a conjugated diene, because of that weak pi overlap. And so we end up with these two different conformations. One of them is called S-cis, and the other is called S-trans. Now this is different from cis-trans. Regular cis-trans is with respect to the double bond. S-cis, the S means with respect to the single bond in between. And so we're doing something different. Usually we were looking at the cis-trans for the double bond, but here we're looking at with respect to the single bond, and we can say that those two groups are S-cis to one another, or those two groups are S-trans to one another. Those are the two different conformations for our conjugated diene. So for S-cis, look at this, steric hindrance, less stable. It's higher in energy. S-trans, more stable. It's a little bit lower in energy, 2.8 kilocalories per mole, lower in energy for us to go to be in the S-trans. So going from S-cis to S-trans, we release some energy because we're making something more stable because of that steric hindrance in the S-cis conformation. Again, S-cis and S-trans are different from cis and trans. Questions on this? All right. Then we'll stop there. We have one more slide with 14-6. We're going to start 14-5. We're going to start 14-6. And then we'll also go into 14-7 and 14-11 on what is it, Friday. So we're going to kind of skip around a little bit as we go through this chapter. All right. So I will see you guys for lab and for office hours. Have a great day. I'm praying for you guys. I love you guys. And I will see you later. Bye.
Thank you.
You're welcome.